Hey everyone, in today's video we're going to look at this mechanism and we're going to answer these questions. Now the mechanism is two discs, they're geared, so there's a gear ratio between them. The larger disc has a block suspended from it and the smaller disc is in contact with a handbrake. So this handbrake we're going to model as a pendulum. This pendulum is pinned on bottom and there's an external force that is applied. We are going to make the assumption that the handbrake remains in contact with the smaller disc. So we're going to say for this problem that there is no rotation on the handbrake. With this handbrake in contact with the disc, there's going to be some friction at that contact point. And of course that friction is going to slow this disc down regardless of which way the disc is rotating. We want to answer these specific questions. We want to answer how long does it take for this system to come to stop, and when it comes to stop, how much has the block displaced? So what is the displacement of the block? Now, understand these questions are inherently about time. One of them asks for time explicitly. The second one is, we're asking for position, but we're asking for the position at a certain moment in time. When you have questions associated with time, usually that means you're looking at an equations of motion problem. So the goal today is to analyze this mechanism, to develop the equations of motion, and then once we get them, we're going to take numbers and we're going to plug the numbers specifically in so that we can get some numerical answers. Okay, let's get started. We know the process for doing equations of motion. We know that we need to do kinematics, and we need to do forces and moments so that we can construct the Newton-Euler equations. Let's start with the kinematics and the write-up. So I called these bodies A, B, this is body C, and this is body D, the handbrake. We can call out, we could do position vectors and then take derivatives. At this point, I think we've all had plenty of practice. We should all be comfortable if I just jump straight to VA dot is equal to 0, because again, the disk is pinned. Same story with VB dot. VC dot, I'm going to say is Q double dot in the y-hat in direction, and VD dot is also 0. And the reason VD dot is 0, clearly this pendulum can rotate back and forth, but we're making the assumption that the handbrake remains in contact. If the handbrake is not in contact, then there is no friction at this point, so that friction is not acting to cause the system to come to a stop. So we can start with these claims about linear accelerations. Next, let's do angular. Well, body A rotates and body B rotates, body C does not. And again, even though the handbrake we're modeling as a pendulum, we're assuming it stays in contact, which means it can't rotate. If it rotates, then it's no longer in contact. Therefore, let's say that omega NA is theta 1 dot ZA. Omega NB is theta 2 dot ZB, and omega NC equals omega ND, and those are both 0. And I did these as omegas. We could, of course, come and put the dots on these, make them omega dots, and clearly that's just going to make these theta dots. Okay, next, let me clean this up a bit, and we're going to go through and we're going to do the constraints. But I think, again, at this point, we could probably just talk about what the constraints are. You should probably, I think you're probably able to just look at it and tell. There's a gear interface, so we're going to have a gear ratio here. And we've seen this kind of assembly several times before. We know that as disk B spins, block C is going to translate. So there's going to be an arc length constraint associated with this interior radius of B. We're going to write those equations down in just a bit, but how many generalized coordinates are in this problem? We have the kinematic write-up already, we have a translation associated with the block, and then we have a rotation of A and a rotation of B. So 3 generalized coordinates. We can see from the diagram there's going to be 2 constraints. So just from observation, we can make the claim that there's going to be 1 degree of freedom. Okay, let me clean this up and I'll get these 2 equations. We said first there's the gear ratio. Radius of A, I will call this RA. So RA theta 1 will equal this interface, gear ratio. We know that when one is positive, the other will rotate negative. So there's a negative sign. And it's on the outer radius of B. Let's say the inner radius of B is RB1, the outer radius of B, RB2. So this gear ratio is RB2 theta 2. And of course, we can take the derivatives of this. RA theta 1 double dot equals minus RB2 theta 2 double dot. Next, constraint for the arc length. As this disk rotates, the block is going to translate. Consider how we defined the position or how we define the acceleration of the block. We said that Q is positive up. So when disk B rotates in a positive direction, the block is going to drop. So the relationship between the rotation of the disk, the angle theta, and then the translation Q is going to be negative. So Q will equal negative, and this is RB1, right? Because the rope is wound around the interior radius. RB1 multiplied by the angle of the disk, theta 2. And of course, we can take derivatives for this as well. Q double dot minus RB1 theta 2 double dot. Okay, we had 3 generalized coordinates. That was Q, theta 1, theta 2. We have 2 constraints. So of course we have 1 degree of freedom. Now, with the 1 degree of freedom, what does that mean for our task in this problem of doing the equations of motion? With 1 degree of freedom, it means that you will have 1 equation of motion. So we should just go ahead and expect that at the end of this process, we're going to have a single equation of motion that is going to govern the motion of the whole system. Okay, let me clean this up and we can move on now to, let's do free body diagrams. Here's the free body diagrams. I labeled the bodies A, B, C, D. Feel free to label them whatever you like. Let's start marking these up with the forces that are present. Now, the easy things, we know that there's gravity acting on each one of these. MCG, MBG, MAG, and MDG. Next, well, there was also that external force. Let me add this, F external. Okay, beyond these, right, we got gravity on there, and then we have an external loading. Beyond those, what's next? Well, reaction forces. There's pin joints, there's a gear interface, there's tension in a cable, there's something going on with the contact points. Okay, let's start with body A, the pin joint through the middle. This will have an X component and a Y component, so R1X, R1Y. Next, let's move through the mechanism, through the discs. We'll come back to the handbrake last. So, what is going on with the interface between the 2 gears? Well, remember we've done interference fit before, and in interference fit, these 2 bodies are actually pushed together, right? And it's usually something like a hard rubber on the outside, and that rubber has been compressed, and then they've been shoved together, which means there's a normal force between them, and there's a friction force between them. Now that's for an interference fit. For gears, what happens, you have your gear teeth and they're pushing against each other. Now, the force of transmission between these, right? Because one of them is going to turn, it's going to push on the other. The force between them will be tangential. There will also be a component of the force that is normal between the two. The normal component for gears is usually fairly small. You will study gears and you'll talk about the components of the force between them when you take your mechanical design classes. You'll do gear design. For now, for today, let's say, let's not worry about the normal component between them, and we're simply going to model a transmission force between the two, between the teeth. And you'll actually see, you could do this analysis and you can go back and you can add that normal force between these. And since it is not a friction, since it is just a transmission force, that component's actually not going to have any bearing in our final answer, but that's okay. So what we're going to do, we just need to model the transmission force between these two discs, and I'm going to label it as if it's just another reaction force, because remember, this is in fact a joint, right? There's and there's even a constraint between these, which means that there has to be a reaction force to enforce the constraint. So I called that one R2. I did it positive or up and right on A, and I did it down left on B. Okay. Next, there's the pin right in the middle of body B, so of course a set of reactions here as well. This is R3X and R3Y. And then there's also the tension in the cable, and this is R4. This is a reaction R4. And I put it at some point away, right? We know that there's two different radii at work. There's the outer radius and then there's an inner. Okay, that's it for B. The tension in the cable R4, it also acts on body C. And of course, just remember we need to maintain Newton's third law throughout the whole problem: action and reaction. Okay, next, let's talk about the interface between the handbrake and gear A. So there's an external force that's pushing, right? That's pushing this thing in, which means there's a contact point between these two. Just to keep it simple, let's say that the contact point is perfectly on the right side of the disc, which means that we're going to say that the handbrake is actually perfectly up and down. This makes it easy to find this contact point in the disc. Also later, it will actually make it easy for the moments, for the sum of moments equation on this handbrake, because it ensures that the gravity creates no moment. And of course, we're assuming that this thing stays in contact. So gravity is going to create no moment there. So this is in contact. There is that means this point between the two, they're pushing against each other. So there's a normal reaction at that location. I called it R5. And since these two diagrams are close, I'm gonna do a single R5. R5 is positive on the handbrake, and I did it as negative on body A. Now, what is the mechanism for the handbrake causing the disc to slow down? They're in contact, and there's the normal force, but the normal force is pointed at the center of mass of the disc, which means it's not going to create any moment. What causes the actual slowdown is friction at that point. So I called it F1, and let me clean this up just a little bit. So I'm going to write there's R1Y again. I did the friction as up on body A. I called it F1, and I did the friction down on body D on the handbrake. Okay, and then also acting on the handbrake. Remember, the handbrake is pinned on bottom, so there is a set of reaction forces here as well. This one is R6. R6Y. There we are. Okay. I think that's it. Gravity. We got R5 included, and the friction, good. We have reactions at the pins. Good, 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 good. Okay. Keep these in your notes. I'm going to erase these, and then one at a time, we'll go back and we'll do each one of these bodies, sum of forces and moments. Starting with body A, there's the diagram. Let's do sum of forces. Looking at the diagram, how many forces? Gravity, 2 R1s, R5, F1, R2, so that's 1, 2, 3, 4, 5, 6. Let's do the R1X, X hat in, and R1Y, Y hat in. Let's say, let's go ahead and get gravity in there, minus MAG, Y hat in. Let's do R5. R5 is acting in the negative, X hat in direction. Let's do friction, so plus F1 in the Y hat in. And what do we need to do about R2? We need a direction for R2. And it's not aligned with the end frame, and don't rotate the end frame to make it align with the end frame, but also it's not aligned with the A frame because the disk is spinning, so the A frame is constantly rotating. The direction of R2 does not change. What that means is, what is best is to make a new frame. It's a non-moving frame, so it's just been offset from the inertial frame by some fixed angle. And let's say that, let's see, I defined it as E frame. So we had bodies A, B, C, D. This direction is X, nope, not XD. This is direction XE, and the radial is YE. And of course, this direction, YE, is going to point from the center of disk A to the center of disk B. So we can use that then to define R2. We can say R2 in the XE direction. Okay, so that's it for sum of forces. Sum of moments. We're going to take the moments on A about A. Now, how many of these forces create moments? Gravity, of course, does not. The reaction forces at the pin joint do not. Reaction force R5, that one is pointed at the center of mass. That one creates no moment. So we're left with R2 and we're left with F1. Those two will create moments. So I will do, let's start with cross products. We need the position vector, and I'm just going to call these points A prime, A double prime. You could go through and you could give them other names if you wanted to. But A to A prime cross, and this will be the friction point first, so F1 in the Y hat in, and plus the position vector from A to A double prime. I'm gonna erase gravity, MAG, there you go. Position vector from A to A double prime, cross. This one is the R2 in the XE direction. Okay. So what are these position vectors? Well, from A to A double prime, this is the radius of A in the X hat in direction. And since we're using R's for all of these reactions, I'm actually gonna write these radii as capital. So RA in the X in direction cross F1 in the Y hat in plus. Now the position vector from the center to this point, A double prime, well, that's also the radius A. And we have already defined the E frame, so we can use the E frame. So this is RAYE cross R2XE. Next, let's take care of these cross products. X cross Y is going to be positive Z, and Y cross X is going to be negative Z. And does that match up with the diagram with intuition? Well, F1, the way we have drawn it, F1 would create a positive moment. And the way that we have drawn R2, R2 would create a negative moment. So, what we're going to get from this, we get these scalars. Radius of A times F1 And we know that these are all in the Z, so I can group them. Radius of A, F1, and then these are minus, so minus RA, and then reaction number 2. And that is in the Z, and we can call it the ZA direction. Okay, write these down. Let's move on to the next one. Sum of forces on B. From the diagram, 1, 2, 3, 4, 5 forces. Let's say, we'll start with the ones at the pin, R3X, Xn, R3Y, Yn. Let's get gravity in, minus MBG, Y hat N. Let's do reaction number 4. This is minus R4 in the Y hat N direction. And R2, well, we used the E frame, and this was YE, this one was XE. So R2 is negative in the XE direction. Okay. Next, let's do sum of moments on B about B. How many of these forces create moments? Reaction forces at the pin, gravity, no moments. We're left with R2 and R4. So let's say that the position vector from B to B prime cross, I did R2 first, so here's R2 X E, and then plus the position vector B to B double prime cross, and now it's minus R4 in the Y hat N direction. Okay, let's get the specifics for the position vectors. B to B prime, it's the point associated with R2, we're going against, right? We're going in the negative Y hat E direction, and it's on the outer radius. So this is RB2, negative RB2 in the Y hat E, cross, the force is negative R2 in the XE. Next, the position vector from B to B prime. So we're going in the negative X hat N direction, and it's the interior radius. So this is minus RB1 X hat N cross minus R4 Yn. Well, there's a lot of negatives here. We could actually just cancel all of these negatives. Negative multiplied by negative is going to be positives, and negative multiplied by negative is going to be positives. Okay. So we take care of these cross products now. We have just the scalars, right? RB2 and R2. It's Y cross X. So this term is going to be negative Z. And this one is X cross Y. So the second term is positive Z. Let's, I can group them together. Let's do the second one first. RB1, R4, and then minus RB2, R2. And that is in the ZB direction, ZN direction. All right. Forces and moments for body B. Let me clean this up, we'll do C. Sum of forces on C, well, there's just the two of them. R4 in the Y hat N minus MCG in the Y hat N. And sum of moments, well, we said earlier we're assuming that the block doesn't rotate, and both of these forces are acting directly through the center of mass. So nice and easy for body C. Okay, let's do body D. Sum of forces on D. From the diagram, 1, 2, 3, 4, 5, 6 forces. Let's start with the pin joint, R6X, Xn, R6Y, Yn, gravity minus MDG, Y hat N. let's say plus R5, that's in the x hat in, minus F1 in the y hat in, and then minus F external, and this one's in the x in. All right, sum of moments. Now, what point should we take the sum of moments about? I don't want to have to deal with the reaction forces at the pin joint. So I'm going to say the sum of moments, let's call this point E. Sum of moments on D about point E. Okay, which forces create moments about point E? Of course, the reaction forces don't, because we're making the assumption that this handbrake doesn't rotate, and we're also saying that the handbrake is perfectly vertical, then the gravity doesn't create moments either. So the only thing left then, clearly F external does. F external is going to generate a positive moment. R5 is going to generate a negative moment, and the friction force will also create a moment. Now, the moment arm for the friction force is fairly small, but the way we've drawn it, it would actually create a positive moment. And this is an interesting point, that the friction creates a moment. We're actually going to see this come out of the math once we're done. But imagine that you're applying a force, right, to create a positive moment, and you're driving the handbrake into the spinning disc. It's possible that the friction could actually contribute. It could actually generate a positive moment as well, and the friction can drive the handbrake also into the disc. And what we're going to find is that if the friction reverses, then it generates a negative moment. So depending on what is happening with this friction, you could actually have it contribute to or take away from the application of force onto the disc. And of course, if we do it right, we'll see that in the results. So we have to account for these three forces. Now, R5 and F1, we're going to say that these forces are applied at the same point. So we need the position vector. Now, because we're taking the moments at point E, we need the position vector from E, and I'm going to call this first point D prime. So the position vector from E to D prime cross, and let's say D prime is this first one. So R5 x hat in minus F1 y in, and then plus, we need the position vector from E to D double prime, and that's the external force, F external minus F external x hat in. All right, let's get the position vectors in there. So from E to D prime, well, we actually need to go left just a little bit, and we need to go up. So I called this, I said negative L1 x hat in plus L2 y hat in. This horizontal distance, this is L1, and then the distance from E to this first contact point, that is L1. So L2. All right. So we went L in the negative x, and we went L2 in the positive y. Okay, so it's this vector cross those set of forces, R5x in minus F1 y in, and then the second position vector plus. So now we need to go E to this point, application point, which means we need to go the same distance L1 in the positive direction, right? We're assuming this, we're assuming the pin is right through the middle, so we need to go L1 in the positive direction, and we need to do a different distance. Let's call this one L3. So now it's positive L1 x hat in plus L3 y hat in. Of cross. The force, this is the negative F external in the x hat n direction. All right, what is going to happen when we perform this cross product? Well, we're going to get x cross y. We're going to have y cross x. So both of those are of course going to be about the z-axis, and then we will have y cross x. And all the other combinations, x cross x, x cross x, those of course all go to 0. Now feel free to do those cross products if you need the practice. I'm going to give you the answer. Sum of moments on D about E. How many terms are we going to get? We're going to get x cross y, so there's going to be one term. We're going to get y cross x, there's another term. We're going to get y cross x, there's another term. The x cross y, these were both negative, so we're going to get positive, and x cross y is positive z. The y cross x, these were both positive. Y cross x is negative z. And then y cross x, this one's negative, and y cross x is negative z. So at the end of all this, we're going to have L1 F1 minus L2 R5 and L3 F external. And then that is Z D. All right. So there's sum of forces and moments for everything. We have kinematics. We have sum of forces and moments. That means we can get started now with the equations of motion. Let me clean it up. We'll get going. We know that we need to use Newton and Euler's second laws, but where do we begin? We have 4 bodies, and we could do sum of forces and sum of moments for each of the bodies. So 8 equations. We said at the beginning, though, the system only has 1 degree of freedom, so there should, at the end of this, only be 1 equation. That can be confusing, right? Where should you begin? What I'm going to say is, when you have 1 degree of freedom, you need to focus in on one of your coordinates. So we had 3 coordinates, q, theta 1, and theta 2. You could choose any of them. I know that in the question it's asking for some kind of motion of q. Just for today's exercise, let's focus on the theta 1. What happens if you focus on a different one? You get the same dynamics, right? Those are the dynamics of the system. There's only going to be one set of dynamics. So whether you focus on a different one of these variables, in the end, if you do it correctly, you get the same answer. If we're going to do theta 1 is the rotation of body A. So that means we should probably do sum of moments on A about A, at least as a starting point. And then we can see how it develops, and maybe we're going to need some of these other equations. All right, let's do sum of moments. A about A equal to the change in momentum A about A. Now, we've defined all of this stuff in the notes. I have the sum of moments. This is RAF1 minus RAR2. That's Z hat A. And because we've done this so many times, we know what the right-hand side is equal to. This will equal IAA omega NA dot. Now, what happened to the cross product term? It's a symmetrical disk doing a simple rotation. We know that the omega cross I omega is going to equal 0. And what is going to happen here? Well, standard assumptions. We're going to say that the disk is symmetric, the inertia matrix is diagonal only, etc. So the right-hand side, we're going to get the ZZ term out of the AA inertia matrix, dyadic, whatever you want to call it, and that's multiplied by theta 1 double dot ZA. All right, so this is literally the equation. It's, right now anyway, it's this simple. I'm just going to rewrite it, theta 1 double dot, and we can drop the z hat a. We could just write it as a scalar equation. So this is equal to RA F1 minus RA R2. So always ask yourself, am I done? Do we need to go any further? Well, remember in previous videos we've talked about when you're done with equations of motion. You have scalar equations, this is scalar. You have the same number of differential equations that you have degrees of freedom. Well, we had 1 degree of freedom, so here's one equation. But remember, you have to eliminate all unknowns. The only unknown in the equation is what you're trying to solve for. So acceleration, that means everything else has to be known. Well, RA, that's just the radius of A, that's a number. Friction, we need some expression for friction, and R2 is a reaction force, which we don't know. We don't know the value of it. So we need to eliminate R2 from this equation. So we're going to have to do something with R2. For now, let's talk about how to model F1. F1's the friction. There's, as we've talked about, all kinds of ways to model friction depending on the setting. For today's video, and there's a reason why I want to do something this simple, but we're going to use this equation. We've done this notation several times. Theta dot divided by magnitude of theta dots. We know that this is going to equal, if you wanted to write it this way, a sine, sig n function of theta dot. If you take theta dot and you divide by magnitude, absolute value of theta dot, you're just going to get +1 or -1. So really, this is just tracking which direction the disk is rotating. If the disk rotates in a positive direction, then F1 is negative. Go back to the diagram. That means if theta 1 dot is positive, that means the friction points down, which makes sense. If the friction pointed up, that would actually contribute to the speed, and it would make it go faster. What happens if the direction reverses? Well, we'll just do a second one. Here we go. The direction has reversed. So here now is theta dot. Well, in this case, the friction is going to reverse. And now you have negative rotation and you have a positive moment created by the friction. So in both cases, the friction is going to cause the disk to slow down. Now, why did I choose this particular model? I chose this model for friction because it's linear. And when we get to the end of the problem, we're going to see that a simple friction model like this, we can work with it very easily. But of course, we'll talk about what to do with a more complicated one as well. So we've got F1 taken care of. We take F1, we put it back in this equation, and lo and behold, there is now another reaction force in the equation. So we took care of F1, but now we got R5. We have to come up with expressions for R2 and R5, and then we're going to take those and we have to put them back into, we can call this equation number 1, the big equation. So whatever expressions we get for these terms, they're going to go back into this. And then if we've eliminated all the unknowns, then we're done. Okay, so how do we get these? Well, we're going to start with R2. Recall that R2 is the transmission force between the two gears, the two big disks. That tells me maybe we should go look at the equations for body B. Here was A, here's body B, and there's R2. Let's look at the equations for B. Now, you've got them in your notes, sum of forces and sum of moments. The sum of forces equation has the reaction forces at that pin joint, and we don't know those reaction forces. So if you do the sum of forces equation, what's going to happen is you're just going to solve for R2 in terms of these two unknown reaction forces. So again, how does that help? What we're going to do, let me clean this up, and we're going to do Euler's second law for body B. Here's Euler's second law for body B. You should have this in your notes already, the sum of moments on B about B. And of course, ddt of HBB Symmetric body, we're going to say the cross product term is 0. So IBB, omega, and B. And same assumptions that we did on body A is going to lead us to IZZBB and theta 2 double dot. And this is about the ZB axis. Okay, what was the point of us coming here? We wanted an expression for R2. Well, we can drop the ZB's, turn this into a scalar equation, and we can simply solve for R2. If we solve for R2, here's what you get. Move this term to the other side, and then we're going to divide by the negative RB2. So dividing by negative RB2, and then it's this multiplied by the right-hand side, IZZBB, theta 2 double dot, and minus RB1, R4. All right, and I've dropped the frames. Now, here's an expression for R2. RBs, these are known radii, inertia is known. Here is another generalized acceleration. And now, this is in terms of R4. R4 was the tension in the cable. We had disk B, we had the tension in the cable, and we had the block. And there's R4. So we can take R2 and we can put it back into equation number 1. And when we do that, now equation number 1 is a function of an unknown R4. So where do we get R4? Well, maybe we should go look at the equations for body C. And I can actually do that. We have enough space. These are small equations. We're going to do sum of forces on C. Remember, there were no moments and body C did not rotate. So the sum of forces on C, we're going to set this equal to ddt of kc. We know what that is. That's mc vc dot. So we've got both of these quantities defined in our notes already. We have the sum of forces and we have the kinematics done. This is R4 y hat n minus mcg y hat n equals mc q double dot y hat n. Okay, the point, we wanted to solve for R4. So let's turn this into a scalar equation, and I can simply move the mcg to the other side, and we're left with R4 equals mcq double dot plus mcg. All right, take this R4, plug it in right here, take that R2 and plug it into the previous equation of motion from body A. I have the answers written down here. I would recommend you try it yourself just to confirm. Check my math anyway. We can do that. Where do we need to go next? Well, we've taken care of the left side of the mechanism, right? We took care of R2 and we took care of R4. That takes care of the whole left side. We still have to find R5. That was the reaction force that was in that friction term. So where should we go for R5? Here is disk A, and here was the handbrake. R5 was the reaction force between these two. Now, we're actually looking for the friction term, but the friction term is a function of R5. So how should we get R5? We need to go look at the equations for body D. Which of the equations should we look at? If we do the sum of forces on body D, then the reaction forces at the pin joint are going to come along, and we don't have expressions for those. So we would simply be solving for R5 in terms of, again, an unknown reaction force. That leaves sum of moments. I want a sum of moments of Euler's second law equation for the pendulum that does not involve these reaction forces, which is, of course, why earlier I defined the moments on the pendulum about the pin joint. such that those reaction forces are not in the equation. Now, what if you had not done that? What if you had taken your sum of moments about the center? Then the reaction forces are in that equation too. You can do that. Now you're solving for R5 in terms of these unknown reaction forces, and we need additional expressions to get rid of those, at which point you go back to Newton's second law, you solve for the reaction forces, you take those expressions, you put them into Euler's second law, and then you can solve for R5. So again, just to highlight how useful parallel axis theorem is. It allows us to get from body D and to immediately find R5 in terms of the other forces, and we never have to mess with these reaction forces at all. Okay, let me clean this up, and we're gonna get started on body D. Euler's second law on body D. I've done some major simplifications. We know that if we're doing angular momentum about an arbitrary point, first of all, there's an additional term that you need to add into the angular momentum term, minus md p d to e cross ve. Don't ever forget about that term. Conveniently in this problem, we're taking the moments and the momentum about point E, which doesn't move, has no velocity. So this term goes to 0. We're also modeling the pendulum as a symmetric body, and it's doing a simple rotation. So again, feel free to go through that algebra. You'll find that the cross product term, omega cross I omega, is also 0. So what we're going to be left with after all those terms are eliminated is we have the modified inertia multiplied by omega into d dot. Now, you might dig in to this inertia term and you might apply the parallel axis theorem, but if you recall, when we did the kinematics, we said that we were assuming the handbrake did not rotate, which means that omega in d dot is 0. So the right-hand side then of this equation is 0 for body D, sum of moments on d about E. For this problem, it's going to equal 0. We already have the left-hand side. I'm just going to copy it down. This was L1 F1 minus L2 R5 plus L3 F external, and that is going to equal 0. We needed an expression for R5. Well, notice this equation has F1 in it, and we wrote a definition for F1. We said that F1 was going to equal minus mu R5 theta dot divided by magnitude of theta dot. So let's take that, let's put it into this equation. Now we've got two R5s, so we group those R5s, we move everything else to the other side of the equation, and we solve. I'll do one intermediate step. So L3 F external was equal to R5, and this is L2 plus mu L1. We'll write as L1 mu. Distance L1 mu theta dot divided by magnitude theta dot. Okay. So what did I do? I want to get rid of the negative, so I move that one to the other side, makes it positive. And then once you substitute this in, this one's negative as well, negative mu, kick that to the other side. All of these terms enter positive, so we want to solve for R5, so clearly I'm just going to divide by this term. R5 will equal L3 F external divided by L2 plus L1 mu theta dot divided by magnitude of theta dot. Okay, here's your R5. Let's take these and we can start adding them back into that very first equation. Before we do though, I do want to just point to this one interesting term that is happening here. The magnitude of R5, so the magnitude of the normal force between the handbrake and the disc. And let's think about this logically. you're applying some external force to this handbrake. You can imagine that you're doing it literally with your hand, like you're pushing a lever. And clearly the harder you push against this pendulum, the greater the reaction force is at that contact point, right? It's linear with respect to F external. Similarly, what if the lever becomes very, very long, or the location of the applied force changes? Well, then your moment arm is going to change. So it's linear with respect to that one as well. L2 was the distance to the location of the reaction force. And notice we're dividing by L2, so you actually want L2, if you're attempting to maximize this reaction force, you would actually like L2 to be fairly low. If L2 is applied at the same location as F external, then they have the same moment arms. With a very long moment arm on the F external, it's going to cause this reaction force to increase. So we would, if that's what we're going for, we would like to divide by a small number at this point. Okay. And then what is going on with this term? Mu is just a number. It's a constant, 0.5, right? 1.1, something. And then L1 is the width of the rod. So there's not a whole lot we can do about that, right? You're probably designing this handbrake, and you might have geometric constraints or something, right? Like this ends up just being a number. So the theta dot then, this ends up being the sine of theta dot. This is just going to switch back and forth between +1 and -1, which means depending on the direction that the disk is rotating, this becomes positive or negative, which means this number will add to or take away from L2. So you can either divide by a larger number or a smaller number. If you're dividing by a larger number, then R5 is diminished. If you're dividing by a smaller number, then R5 is increased. Okay, if the disk is spinning in a positive direction, here's the disk, and the disk is spinning in a positive direction, what happens? This is positive, right? And then this adds, and that makes the denominator larger. So R5 is diminished. When your disk is spinning in a positive direction, it's going to reduce the reaction force here. It is actually kind of kicking the pendulum away from it, okay? The friction at that point would create a slightly positive negative moment to take this pendulum away. What happens if the direction of the disk reverses? Now the disk is rotating in this direction. Well, if the disk is rotating in this direction, a negative spin, then we need the friction at the surface is going to be positive because it opposes the motion, which puts the friction on the pendulum negative, and we can see that force pointing down on the left surface would create a positive moment on the pendulum. That positive moment on the pendulum, it's small, right? It's a function of just these widths, but that little bit of friction right there would actually pull the handbrake onto the disk, and it's actually going to increase the reaction between these two. So there are times when the rotation of the disk can actually lend itself to the handbrake, or the rotation of the disk could oppose the handbrake. So if you're in a situation where you are designing one of these systems, and you have a choice then on which side of the disk do you apply the handbrake, understand that if you want the handbrake to be effective, there is a correct choice. Assuming that both options are available, you choose the side of the disk such that the friction actually pulls the handbrake onto the disk, if that's what you're going for. Okay, we have these expressions now. Let's take them all back to equation number one. We're going to put it all together. We're back at equation number one, the equation of motion for body A. This is what we had from before. I have substituted in the expression for friction, so we can see that we need to replace R2 and R5. Take those definitions that you've already written in your notes and put them into the equation, and what you get is you get this whole thing. So this is what you get. I had to write in 2 lines. I ran out of room. And what I've also done is I've done one replacement. I've put in an intermediate variable alpha, and I'm letting alpha represent mu, and then theta dot over magnitude theta dot. So this term now, right, this is our equation of motion. So we ask ourselves, are we done? Is it scalar? Yes, it's scalar. We had 1 degree of freedom, right? We have one equation. Have we eliminated all the reaction forces? Yes. This has no reaction forces in it. So, are we finished? Well, what are we attempting to solve for? We want to solve for an acceleration. Well, this equation has 3 accelerations in it. Theta 1 double dot, theta 2 double dot, q double dot. So what do? We only have one equation. We can only solve for one unknown. That means that we need to replace the theta double dot, theta 2 double dot, and q double dot with expressions of theta 1 double dot and then collect terms. So how do we do that? How do we solve for a generalized acceleration in terms of another generalized acceleration? Well, we use the constraints. So we wrote down the constraints back at the beginning. Go back and look at them. We had the acceleration level constraints. That means we just need to take those equations and do a little algebra and solve for theta 2 double dot, and here it is, minus RA over RB2, theta 1 double dot, and we need to solve for Q double dot. Now with Q double dot, you have to use both constraints. So you solve for Q double dot in terms of theta 2 double dot, and then you use the same equation from above. And for Q double dot, we have RA, RB1, RB2, theta 1 double dot. All right, here's what's gonna happen next. I'm gonna erase, and I'm gonna come back and I'm going to take these, I'm going to put them into this equation. When you put them into this equation, what's going to happen? The Q2 double dot is going to equal this, which means you now have Q2, theta 2 double dot is going to equal this, which means you now have a theta 1 double dot on the right-hand side. Take that term, bring it to the left. And what's the sign going to be? Well, right now it's positive, and once we use the constraint, it's negative, which means you move it to the other side and it's positive again. So these two components are going to add. Next, the Q double dot term, it's already negative. We have our constraint sorted out. You're going to have theta 1 double dot in this term. You move it to the other side. It's negative, it becomes positive. Everything else on the right-hand side is going to be the weight of the block, and then also this effect of the external force modified by the friction term. Okay, and when we do that, here's how I'm going to present it to you. I'm going to present the equation as A Q double dot equals B. Q double dot, sorry. We're doing this one for theta, so A theta double dot is equal to B. Okay, let me clean all this up and I'll give you the final answer. So here's the final form. I've written it as A theta double dot equals B. Clearly we can solve for theta double dot, B minus A. Since this is since it's a scalar equation, it's not a system of equations. We don't have to invert A because it's not a matrix, so it's just simple division. So A over A and B are equal to these terms. Now, again, how did I get this? I took those constraints, I put them into the equation, and then I organized, right? I moved everything with the theta double dot, theta 1 double dot. Everything with the theta 1 double dot to the left, and then I grouped terms. So let's look at the equation and let's make a little sense out of it. The acceleration of the disk. Mass and inertia are resistances to changes in the current state. So the role of mass and inertia then are resistances to changes. The body wants to stay at equilibrium, and the more inertia it has, well, you're dividing by those inertia terms, those inertia and mass terms. So that is your resistance to change. And notice that it's all positive. So the inertia of disk A, the inertia of disk B modified by the gear ratio, and also the mass of the block modified by the gear ratio. All of these things are resisting change in their current state. So they all add together through some weighting system that comes out through the constraints. The right-hand side, B, these are going to be the moments acting on your disk. So I've grouped them into two. The one on the left is coming from the gravity, right? The weight on the block, gravity of the block being modified through those gear ratios. And notice that the sign is negative and this number is constant, right? This isn't a function of any kind of states or angles or positions. This is a constant number and it's negative. Why is it negative? Well, we can go back to the diagram for the system, and the weight of the block wants to pull the block down, which means that it wants to make disk B rotate in a positive direction, and disk B would then make disk A rotate in a negative direction. So the weight of the block is creating a negative moment on the disk, regardless of what the system is doing. We're trying to bring this system to a stop, and we can see that the weight of the block is causing this disk to accelerate in the negative direction. That means that if your disk is rotating in a positive direction, the weight of the block is actually contributing. It's helping you stop your block, stop your disk, your system. If disk A is already rotating in a negative direction, the weight of the block actually would make disk A accelerate. If everything else being equal, if there was no external force applied, the weight of block C would make disk A accelerate in a negative direction. So that makes sense. And then the second term, this is the moment created by the external force modified through the handbrake and including the effects of friction as well. And we talked a little bit about how alpha is going to be positive and negative. It'll trend with the sign of theta dot. So if theta dot is positive, alpha is positive, and there's a negative in front. So if theta dot is positive, this term is negative, which would make theta dot slow down and bring the disk to a stop. If theta dot was negative, then alpha is negative. And negative would make this term positive. So if theta dot is negative, this becomes positive, and that will make it slow down. And of course, we also mentioned the fact that alpha appears in the denominator as well. So depending on how the disk is spinning, it could contribute or take away from the magnitude of the reaction force, right? And thus the effect of the applied external force. So what do you do with these equations? Well, one thing we can do is we can put numbers in and we can analyze the system. We could take this theta double dot, we could numerically integrate it using software tools if we needed to. We have some videos out there where you can see how you take the differential equations and you put them in MATLAB and you numerically integrate them. What we're going to do right now is take these equations, make sure you have them written down, and what I've done is I've come up with some assumed values for all of the constants. You take a look at these equations, there's nothing but constants in it now. The inertia terms, the mass, these radii, all constants. Mass, gravity, all constant. Lengths, L1, L2, L3. The applied force would be specified. And then recall that alpha was mu theta dot divided by absolute value magnitude of theta dot. Now, here's why I chose this particular friction model, because this friction model is linear. And what we're going to do in a minute is we're going to actually analytically integrate this whole system. So if, well, we'll see when it comes out. Okay, so what I'm going to do is make sure you have these. I'm going to erase, and I'm going to put the values that I've assumed on the board. Here's the values I came up with. 3 radii, 3 lengths, 2 inertias and a mass, and then specify the external force, coefficient of friction, and we also have to provide some initial conditions. or at the very least, we need to know the direction that this is rotating. And if we want to, if we actually want to solve for the time required to stop, then we're going to need to use this. Now, we take all of this, we put it into the equation. We said theta 1 double dot is b divided by a. I called this c, and the number I calculated was negative 3.58, and that is radian per second squared, right? Theta double dot. So you can change these values if you like. Feel free to copy those equations and put in different numbers. Here's an interesting point though. The way that we did the friction model, we said friction was negative mu theta dot divided by absolute value of theta dot. Recognize that this friction, it's not actually a function of the value of theta dot. It's only a function of the sine of theta dot. So it's actually negative mu multiplied by 1 or negative 1. Hey, what are you going to do? Go. You're welcome. Okay. The friction is a function of the sine of theta 1 dot, not the magnitude of theta 1 dot. That means if I had changed theta 1 dot, I had gone from 20 to say 30, the magnitude of the friction would have been the same. And if I don't change any of these parameters, then the acceleration remains the same. I selected this friction model specifically because it is not a magnitude of, it's not a function of the magnitude of theta dot. The acceleration then, it's negative 3.58 when we're at 20 radians a second, at 10 radians a second, at 3 radians per second. And for what we're about to do, that's useful. So we could calculate a number for C. We change these, we get a different C, but it does not change with theta dot. Okay, because it does not change with theta dot, we can analytically integrate and let's say that theta double dot is equal to C. C is a constant. It doesn't change with time because the value that is changing with time is the theta dot, and as theta dot changes with time, C does not. Okay. We can analytically integrate these equations. So let's integrate both of them with respect to time, dt. And when we do this, we're going to get an equation for theta dot as a function of time. Integrate the first side, you get c times t plus some integration constant. The integration constant will be the initial angular velocity, so theta dot at time 0. Integrate this again. Theta, this is theta 1. So theta 1 as a function of time, 1/2 c t squared plus theta dot at time 0, theta 1 dot at time 0 multiplied by time, plus the initial condition, which is just your initial angle. So theta at time 0, which I'm going to call 0. All right. We were able to do this analytical integration because C does not change with time. What if our friction had been mu theta dot over magnitude theta dot again sine, and then if there was something else where it was like theta dot squared, something like this. This means that the friction force would change with time, right? Because the value of theta dot would change with time. If the friction force changes with time, then this is no longer true. You cannot simply analytically integrate this because the value of C itself is a function of time. If you have more complicated friction models like this, or if your differential equations then are just, right, like it's not just some constant acceleration, what do you do? How do you solve it? Okay, you put it into software and you numerically integrate. This is what we end up doing with real-world systems. It is very rare that your system is linear enough that you can actually perform an analytical integration. So at the end of the day, we just numerically integrate stuff, our actual problems. But let's stick with this and let's just see what answers we get. So recall what the original problem was. There was question number 1, and question 1 was how long until the system stops. And then question number 2 was the displacement of the block. So I can write the displacement of the block. I can just write this, let's call this T final, TF. The second question, the displacement of the block, that's really asking what is Q at the time T final. So we have these equations now. How do we go about answering these questions? How long until the system stops? Well, when the system stops, what's the value of theta dot? 0. Here's an equation for theta dot. If you take this equation and you say, okay, well, I want to know what time it is when the system comes to a stop. So 0 equals CT plus theta dot, theta 1 dot T initial. All right, what are we going to get? We're going to get TF, and this is now TF, right? We're saying at the final time, the velocity is 0, solve for time. So TF is theta 1 dot, that initial value divided by C, and it's a negative on it. And the negative makes sense because we had a positive theta 1 dot initially, and we had a negative acceleration, so the negatives cancel, and we end up with positive time. Okay, so that answers the first question, how long until the system stops? Solve for final time. Question number 2, what was the translation of the block at final time? Well, we have an equation for theta 1, and I can take this value of final time and I can plug it into this equation, right? And then how do we go from theta 1 to Q? Use the constraints. We have the equations for it. So I took all this math, I put it into MATLAB, and I will give you the answers that MATLAB gave me so that if you like, you can go and you can plug this into MATLAB and confirm my number. So T final is 5.58 seconds. I also solved for theta at the final time, and that one came out to be 55.8 radians. And then our Q at the final time was 37.2. Okay. And again, the values we put into this system to get that, I said that theta 1 dot at time 0 was 20 radians per second. Okay. So the specific problem statement, it didn't say, give me the equations of motion. The problem statement was asking things about time. How long does it take for the system to come to a stop? What are the values of the states at a certain moment in time? When you have those questions, you need to understand that those problems are inherently equation of motion problems. If you can analytically integrate them, cool, do it. If you can't, you take this second order differential equation, you numerically integrate it, and then you look at the time history of these states to answer your questions. Okay, that was fun. I hope you're all doing well. I will see you next time. Best of luck.